Today is an auspicious day for RIOS and for all those joined in ROS 2023 right now. We are blessed and honored by the man who revolutionized industry and the biomedical sector through his groundbreaking invention of carbon dioxide laser. We, the Indians, are proud of the legend Professor C.K.N. Patel. Most respected Professor C.K.N. Patel, founder, CEO, and president of Pranalytica Limited. Respected professors, members of Raman International Optronics Society, RIOS, friends, organizing committee members, students, and esteemed participants of the webinar. Gaining impetus from the overwhelming support and participation we received from the Global Optoelectronics Fraternity to Raman Optronics webinar series ROS since 2020, RIOS is organizing the 4th Virtual International Conference ROS 2023 from 7th November to 30th November 2023 in association with the Department of Optoelectronics, University of Kerala, India, and Laboratory of Environmental and Life Sciences, University of Nova Gorica, Slovenia. The RIOS was formed with the vision of global interaction and sharing of knowledge in photonics, optoelectronics, and optical communication, with a mission to provide a platform to bridge the gap between academia and industry through collaborative research, webinars, and research paper presentations. Today, we are fortunate to have an eminent professor, Professor C.K.N. Patel, who needs no introduction. He is the inventor of carbon dioxide laser with us as the speaker. Professor C.K.N. Patel is widely recognized as a pioneering figure in the realm of laser technology. He is renowned as the inventor of carbon dioxide laser and several other high-power gas lasers, making a significant milestone in the field. We are thankful to you, sir, for accepting our invitation to the webinar. On behalf of RIOS, I welcome Professor C.K.N. Patel to the webinar series. I also extend a warm welcome to the esteemed professors, researchers, students, and all those who have joined us for the 5th webinar of ROS 2023. I invite one of the secretaries of RIOS, Dr. M. S. Swapna, Laboratory of Environmental and Life Sciences, University of Nova Gorica, Slovenia, to introduce the speaker and to chair the session.
Thank you, Shankaraman sir, for giving me an opportunity to chair this session. It is my great honor and privilege to introduce Professor C.K.N. Patel. Dr. Patel, a visionary in the field of engineering and laser technology, was born in Baramati, Maharashtra. He pursued his Master of Science and Doctor of Philosophy in Electrical Engineering at Stanford University. In recognition of his outstanding contributions to science and technology, he was granted an honorary doctorate of science from the New Jersey Institute of Technology in 1988. Professor Patel is widely acknowledged as a trailblazer in the field of laser technology. He serves as a founder, CEO, and president of Pranalytica Incorporation Limited, a Santa Monica-based company that specializes in the commercialization of high-power quantum cascade lasers and high-sensitivity and selective trace gas sensors. These innovations find applications in various sectors, including commercial, homeland security, and defense markets. During his tenure at Bell Labs, he played a pivotal role in the development of critical technologies for optical communications. He is renowned as inventor of the carbon dioxide laser and several other high-power gas lasers, marking a significant milestone in this field. His research at AT&T Bell Laboratories laid the foundation for high-power molecular lasers, infrared nonlinear optics, ultra-small absorption measurement techniques for gases, solids, and liquids, and the emergence of laser surgery as a viable medical technique. He has authored or co-authored over 270 publications and has been awarded 60 US patents. He received the National Medal of Science given by the President of the United States in 1996. In 2012, he was honored with induction into the National Inventors Hall of Fame, a testament to his transformative inventions. Dr. Patel was elected to the National Academy of Sciences in 1974 and to the National Academy of Engineering in 1978. His contributions to the field of laser surgery led to the honorary memberships in both Gynecological Laser Surgery Society and the American Society for Laser Medicine and Surgery. In 2018, the American Laser Study Club established the Kumar Patel Prize for Laser Surgery in honor of his invention of the carbon dioxide laser and its critical importance in laser surgery. He was named the first recipient of the prize. He is the past president of the American Physical Society and Sigma Xi, the Scientific Research Society. On behalf of all the RIOS members, I welcome you, Professor, to this webinar. And I also welcome all the invited guests and participants to the webinar. Now, I kindly request Professor C.K.N. Patel to begin the presentation.
My talk is about the history and how things happen, as opposed to something that has happened very recently. As you know, carbon dioxide laser has been around since 1964, and often the history gets forgotten. And I thought it will be a good idea for us to, for me certainly, to go back and revisit how all of this thing happened. So the title of my presentation is The Genesis of the Carbon Dioxide Laser and How It Changed the World of Lasers. The plan of my talk is given in this slide. After the introduction, I will go through a personal history of the start of the high-powered laser era, which is a CO2 laser. I will then walk into the area of applications of CO2 lasers, say a few words about other molecular lasers, and then I'll say towards the end, I'll take on something that's new, which is a quantum cascade lasers, which is what I've been working on for the last almost 15 or 17 years. But that part will be fairly short. The talk is primarily about how the era of high-powered lasers began. So let us start with how the ride on the high-powered laser horse began. As all of you know, lasers were invented in 1958 by Shawlow and Towns in their seminal paper in Physical Review. The first operational laser happened in 1959, which was pulsed ruby laser made operational by Dr. Maimon. First gas laser happened in 1961, which was the helium neon laser, and Javan and his colleagues at Bell Labs were responsible for it. However, none of the lasers met the expectations of high power. At that time, there was an enormous excitation amongst the community to what one can do with very high powers, science, death ray, and everything else. But with the powers available in 1961, this certainly couldn't have been done. So the march towards the high power started in 1964 with the discovery of laser action on vibrational rotational transitions of molecules in 1963. If we go back a little bit, the status in mid-1961, which was when I joined Bell Labs, having done my PhD at Stanford, there are only 5 gas laser lines available, all near 1.1 micron. Only atomic system, this is neon, showed inversion. And there was a strong belief that a close coincidence between metastable state of one atom and upper laser level in another atom was necessary for the laser action to occur. In mid-1961, there was only one solid-state laser, ruby laser. And as I said, and it was commonly held belief at that time that for high-power lasers, gas lasers will not be able to compete with solid-state lasers. If we move to a time span from 1961 to 1963, I showed that helium neon was not unique. You do not need close coincidence between energy levels of 2 different gases to have a laser action. What I showed was that all noble gases, neon, argon, krypton, and xenon, showed laser action. And by 1963, several hundred new laser lines were discovered. Many types of lasers came about by the time of 1963 rolled along. Gas lasers, as I just mentioned, optically pumped solid, ruby, and others, optically pumped dye, and semiconductor lasers. But there was no sign of continuous wave or average power output greater than tens of milliwatts. So lots of lasers, but not a lot of power. So in mid-1963, this was the status. Gas discharge was shown to be a universal mechanism for population inversion. More than 1,000 new gas laser lines were discovered. All noble gases and many other elements were made to layers, and solids now more than ever were the choice of high power for getting high power. This was the time when we found everything would work, but nothing seems to work, in the sense that no laser produced more than tens of milliwatt of average power. So at this time, new thought process was absolutely necessary. Forget about solid-state lasers, forget about traditional gas lasers, and you need to have something different. And what I did was I moved to molecular laser systems, especially vibrational rotational transitions. Here is the reason why. What I show in this slide are energy levels of helium neon and carbon dioxide. Helium neon, the lasing action takes place in neon, as shown here, from 3s states to 3p states, or 2s states to 2p states, at either 6328 nanometers or 1.15 microns. The thing to notice here is that you need to excite a neon atom from ground state to the upper laser level at either 2s or 3s, which is roughly at about 20 electron volts. And then you get a photon out at either 6322 angstroms or 1.15 microns, roughly 1 or 1.5 eV. So the fundamental quantum efficiency of the system is very low. It's of the order of 5 to 10%. If you look at the vibrational rotational transitions of carbon dioxide, they all fall between from here to here. So instead of having to excite the carbon dioxide neon to this high level, you have to excite carbon dioxide only to roughly about 0.3 eV. You can get I assume I expected to get laser action at 10.6 microns, which is roughly 1/10 of an eV. So you have quantum efficiency of almost 40%. So what happens here is that you have a significant advantage in inherent quantum efficiency. There was a key insight, and there are several other insights that led to the revolution. Laser center density is important, which is what all the solid-state laser people kept on saying. But volume is equally important. You can make up by lower level of lasing center density by having larger volume. What's critically important is thermal management. One can always supply a lot of laser power, a lot of pump power, but removal of waste heat is the most critical. With gases, we have one more knob to turn. You can flow the gas for thermal management. So both from the point of view of inherent quantum efficiency and removal of the thermal management, gases were significantly important than solid-state lasers. So as we move to molecular lasers, there is of course a complexity. Each vibrational level, for example, the 001 level of carbon dioxide consists of many rotational levels. Similarly, the lower laser level, 100, also has multiple rotational levels. And what you find is that the output will occur not only on a single transition, but on multiple laser lines separated by roughly 60 gigahertz for carbon dioxide. The important thing to remember here is that we need to have efficient excitation to the upper laser level and efficient emptying of the lower laser level. Whether you go to 10.6 micron, which is this radiation, or 9.6 micron, which is this transition. So before I go any further, I'll jump significantly further ahead and give you a quote from a plenary speaker at Fiber Lasers meeting at the SPI meeting on September 5, 2019 in Strasbourg. The speaker said, in 1964, to the great consternation of all solid-state laser people, someone upset the apple cart and broke the 1-watt power barrier. And that was, of course, the carbon dioxide laser. So what happened in 1964? I published 2 papers. First one was laser action in pure carbon dioxide. So the interpretation of CO2 optical laser experiments. This was in April of 1964. And a second paper, which was selective excitation to vibrational energy transfer in nitrogen carbon dioxide. And mid-1964, the nitrogen carbon dioxide laser produced more than 100 milliwatts of power output. I left a late night note to my assistant Rudy Curl saying, Rudy, I got 0.75 watts out last night. This was a major breakthrough, and that started the whole process from getting very little power to lots of power output. So this was my proposal. Energy transfer between molecules. To get more laser power, you need to excite CO2 to the upper laser level faster. Find a molecule that stores vibrational energy, and the level is very closely matched to the CO2 upper laser level. By that time, it was known that nitrogen in a low pressure discharge will have somewhere close to 30% of its nitrogen of the molecule excited to V equals 1 level. This is metastable state, and so once the electron collision excites the molecule to that level, it cannot decay by radiation. What you find is that there is a very close energy match between the upper laser level in carbon dioxide and the vibrational level V equals 1 in nitrogen. So this was an obvious choice. You mix carbon dioxide and nitrogen, run a discharge to see if there is an improvement in the laser action. Here I show, on this slide, I show my lab notebook photograph of my first way of deciding if there was a good energy transfer between nitrogen and carbon dioxide. The one on the left-hand side shows a sketch of it. What it was that there is a vacuum pump that evacuated the laser region. There are mirrors here. There are mirrors here and here, and nitrogen comes in through the central port, flows through here. There is a discharge here. Carbon dioxide comes in through a separate port. There is no discharge here, and there is no discharge in the interaction region. This was the only way one could be absolutely sure that nitrogen was effective in transferring its energy to carbon dioxide. What we found was that even with no discharge in the interaction region, the vibrationally excited nitrogen, which came from this area, transferred its energy to carbon dioxide, and laser action took place in carbon dioxide. Notice there are two things that I discovered in this particular aspect in one manner. One is that the energy transfer from nitrogen to carbon dioxide is very effective, and that's one. Number two, that if you can produce vibrationally excited nitrogen by any process other than electrical discharge, you can have laser action in carbon dioxide. All you need is a vibrationally excited nitrogen molecule. That eventually led to the gas dynamic laser, where one would heat nitrogen thermally, expand it adiabatically, and mix it with carbon dioxide to produce a gas dynamic laser. I was not involved in it, but this was the beginning of the idea that all you needed was vibrationally excited nitrogen, no matter how you produce it. So this is what happened in mid-64. Constructed an apparatus, and we began the study of energy transfer from nitrogen to carbon dioxide. As usual, the whole day was spent in preparation, and started experiments at 9 p.m. My assistant had gone home by that time. At 1 a.m. in the morning, something magical happened. The power meter that I was using for measuring power output maxed out. It reached the maximum. I thought the power meter was faulty. Remember that this is late 1964. No lasers produce more than 100 milliwatts of CW or average power. Power meters in this age were typically aptly thermophile, very accurate, but they maxed out at 100 milliwatts. So not knowing what to do, I put my hand in the beam. And surprise of all surprises, I got a very severe laser burn on the back of my hand. Then I knew that I had done something truly earth-shattering, but without a power meter, how would I know how much power we had? So what I did was invention. I found a small beaker, filled it with known quantity of water, and directed the laser beam into the beaker while measuring the water temperature. You measure the time accurately, you measure the temperature very accurately, and what I found was that the laser power was 15 watts, continuous wave power of 15 watts. Now this is 2 a.m. by this time. I have a problem. Who do I find to witness the first high power laser? I found a janitor in the hallway. He was cleaning the corridors. I asked him to come witness my procedure. Went through all the steps as before. When all done, the janitor agreed that he had witnessed the experimental results and certified them. But before leaving, the janitor turned around and said something insightful. Doctor, there are easier ways of heating water. Well, that's one way of looking at the issue, but I clearly had broken the 1 watt barrier and reached 15 watt before the end of 1964. So the vibrational energy transfer from nitrogen to carbon dioxide works quite efficiently. But now the problem is emptying the lower laser level, 100 or 020, which will then decay down to 010, and you eventually have to return to the ground state. What we found was adding helium to depopulate the lower laser level was very, very efficient. And that eventually led to the first 100 watt carbon dioxide laser. This was a picture taken in early 1965. I'm standing here with the laser. The laser runs from back to here, and the output comes out at this point. And this is what started the entire horse race of high power systems. There are two paths for progress subsequently. Further development of carbon dioxide lasers for higher power, which was carried out primarily by Defense Department and defense and aerospace companies. By increasing the laser volume, increasing the gas flow speed, leading to the gas dynamic laser, and either going to other high power molecular lasers, including chemical lasers. Simultaneously, there was also productization and commercial activity. Commercial opportunities for high power continuous wave lasers were waiting since day one of lasers, since 1958. So this was truly a godsend invention. There was a very rapid entry of carbon dioxide laser into the marketplace. First commercial CO2 laser for sale occurred in year-end 1965. Within 6 months of our showing that there was hundreds of watts of power output was possible. This was a 10 watt laser produced by Perkin-Elmer, and rest is history. You can see what happened in 1966. Defense Department at Redstone Arsenal in Alabama basically reproduced my 100 watt laser by making it 10 times long and generated 1 kilowatt of power output. Things improved significantly. This is a transverse flow carbon dioxide laser, which produced something of the order of 10 kilowatts. And now we have 10 to 20 kilowatt class carbon dioxide lasers, which are commercially produced by Trump in Germany, which are used for many, many applications. And I'll go through some of these applications very quickly. So here is what I call galloping advances in laser power. Carbon dioxide laser, starting from roughly 100 milliwatt very, very low with the first operation to 1 watt to 100 watts, which is what I had done, and then rising to something of the order of several hundred kilowatts by the time we reached 1985. The defense applications are clearly in the range of kilowatt to 100 to a megawatt. Medical applications are in 10 to 100 watts, and industrial applications go from 10 watts to roughly 10 kilowatts. So what did we do? There is new science that was waiting to be done using carbon dioxide laser, which is nonlinear optical research in the infrared, second harmonic generation in materials like tellurium, which was my invention, gallium arsenide, zinc selenide, and others. Invention of third order nonlinearity, or discovery of third order nonlinearity from field electrons in semiconductors, and tunable stimulated Raman scattering from electrons in indium antimonide in a magnetic field. This was a spin flip Raman laser, first tunable laser in the infrared. A CO2 laser pumped spin flip Raman laser tunes from about roughly 8.5 micrometers to roughly 14 micrometers. CO laser, which I have not said anything about yet, but CO laser is another laser that was also my discovery. Can pump spin flip Raman laser, same Raman laser, where we get tunable laser energy from 5.2 micrometers to 7 micrometers. Something that is happening very recently, which is the wake field acceleration of electron to GeV energy using carbon dioxide lasers. And this raises a potential for tabletop GeV accelerators rather than having 2-mile long accelerators. Hasn't happened yet, but it is bound to happen in the next 5 to 10 years. So let's turn to technological applications of infrared high-power lasers, specifically carbon dioxide lasers. First is materials processing for metals, cutting, drilling, welding, heat treatment, and others. And this is a great application in automotive industry. Cutting is especially important for materials which are hard to cut, such as titanium. Titanium, being very hard material, is hard to cut. You either need to use oxyacetylene torch or something, and of course, CO2 laser turns out to be the ideal way of cutting the titanium metal. This slide shows a titanium metal sheet being cut using carbon dioxide laser. Turning to automotive applications, the biggest application is in the laser welding of what is called the white body, everything that goes outside the engine of the system. These are a couple of slides that I have received from Daimler. Now it's no longer Chrysler, but Daimler-Benz. And this is the S-class Mercedes-Benz roof panel welding, which is welded using carbon dioxide lasers. The next slide shows some of the details of how it is done. It's a CO2 laser producing 3.2 kilowatts, welding velocity 2.5 meters per minute, so very fast. Filler wire is 8 millimeters diameter, and you get a continuous beam, roughly 1.3 meters to the side, welding with filler wire, online process monitoring. And laser welding turns out to be stronger than the material itself. So there is clearly an improvement in the joining system by using lasers as a way of doing things. Materials processing, fabric cutting using CO2 lasers has turned out to be a very large application, principally because if you have tried to cut several layers of cloth using scissors, you know what happens. There's a slippage, and so not all layers come out of equal length. CO2 laser cutting turns out to be ideal. It has additional advantage. If you are cutting fabrics made out of some of the nylon or something like that, the ends are automatically sealed because it is by melting, and so you have no fraying at the end. So fabric cutting has turned out to be a major activity. Wood carving is yet another activity. and I would not go into the details of that. What I would like to say a few words about what I call a nutty application of CO2 laser. I invented a system for selling nuts using carbon dioxide laser beam. Some of the nuts, such as macadamia nuts, have very, very hard, very hard shell. And what you find is that it's almost difficult to remove that shell by anything other than really beating the nut with a hammer, which would also destroy some of the nuts. What I showed that you could use a carbon dioxide laser, rotate the nut around its axis, and make a very nice cut. And the laser, you get a very beautiful cut, no damage to the nut itself. Unfortunately, this never caught on. What caught on was similar application for peeling potatoes. I won't go into the detail, but peeling potatoes is a very big business and very big application of carbon dioxide laser. If we look at the application of carbon dioxide lasers in semiconductor fab lines, these are the fab lines that produce integrated circuits. It is used for X-ray production for lithography. Use of high power lasers for production of X-rays from tin droplets, and a company called ASML in Holland is leading the way for continuing progress towards finer dimension lithography. They commercially sell a CO2 laser driven X-ray lithography machine for several hundred $1 million. For medical applications, CO2 laser has turned out to be also a godsend laser. Surgery, soft tissue surgery, tumor removal, cervical cancer treatment, and many others. A very recent application in the last 4 or 5 years is frenectomy. It is surgery for tongue-tied condition called ankyloglossia. It's the most recent application which has a major impact on health of infants. Also, CO2 laser is used for non-invasive diagnostic, for teeth whitening, and also in veterinary medicine. I would like to show you a quote from the award of Kumar Patel Prize in Laser Surgery. This was a quote when I received the prize from that organization. The quote says, "The CO2 laser, invented by Dr. Kumar Patel in 1964, has become the most popular soft tissue surgical laser across all specialties of medicine, ranging from cosmetics, skin surgeries, to dentistry, to ENT, to OBGYN, to oral and maxillofacial surgery, to veterinary surgery and beyond." In the defense area, it is clearly a tool of destruction. Tactical high energy laser, THEL, for destroying incoming Katyusha rockets, as for target designators, identify friend or foe beacons, and for infrared countermeasures. Death Ray Air Force constructed a carbon dioxide laser, a gas dynamic carbon dioxide laser that produced roughly 350 kilowatts of continuous wave power output at 10.6 microns. This was called the Death Ray laser. It was supposed to have gone on an airplane, never quite made it, but at least on the ground, it did produce a very large amount of laser power. High power lasers, especially infrared lasers, are used for trace gas sensing, detection of gases at parts per billion level in presence of interference. Environmental monitoring, semiconductor fab line quality control, non-invasive diagnostics of many diseases, including fever, kidney and liver dysfunction, diabetes, cancer, and biological response to toxic gas exposure, detection of chemical warfare agents, and also detection of explosives. Laser-based gas sensors don't require a lot of power. The wavelength depends upon the target molecule. Optical absorption depends on the target molecule, and heavy molecules such as propanol, ethanol, etc. have broad features, while light molecules such as HF, HCl, NO have very sharp features. Sensing gas molecule in clean air background is different from sensing a target molecule in real environment. So just having a lot of power will not work. What you require is laser tunability in a general case. What are some of the examples of laser-based gas sensors for environmental applications? Nitric oxide detection using CO pumped spin flip Raman laser for parts per billion level measurements of nitric oxide in urban environment, parts per billion level measurements of nitric oxide in the stratosphere. This shows the experiment that we carried out in 1974, putting the entire measurement apparatus in a closed volume and lifting it up to 100 kilometers into the stratosphere for real-time measurement of nitric oxide. If you recall, nitric oxide, almost similar to the ozone, is a catalytic destroyer of ozone. And so if one injects nitric oxide in the stratosphere, that is not a very desirable thing to do. And one of the outcome of these measurements was that the supersonic transport, which was supposed to have flown at 100,000 kilometers, 100 kilometers over the ground, they never got off the ground. Detection of ammonia, SO2, and methane. Detection of ammonia is important for integrated circuit manufacturing in clean rooms. So is SO2. Detection of, you can use laser-based detection of isopropyl alcohol, water vapor for feed gases in the semiconductor application, and silicon tetrafluoride for endpoint detection in IC manufacturing. However, future applications will require and did require new sources. Even if it's a broadly tunable CO2 laser, it produces only about 80 discrete laser lines. CO2 lasers cover only from 9 micrometers to 11.5 micrometers. Absorption features of many toxic industrial chemicals, explosives, and mustard gases are somewhat shorter wavelengths. So CO2 laser-based chemical warfare agent sensor can meet the sensitivity and false alarm requirements, but the sensor is too bulky. I'll return to the quantum cascade lasers a little bit later, but I can point out that quantum cascade laser can meet these requirements. So what happened with the other high-power gas lasers in this region? There is a very rapid exploration of other molecules, CO, now it is commercially available, N2O, CS2, and so on, and chemical lasers, showing that vibrational laser action, vibrational rotational transitions of molecules are very efficient for generating laser action, led to many other lasers as you see here. The other molecular laser that I invented took almost 50 years to mature. This is a carbon monoxide laser. The first publication of carbon monoxide laser occurred in 1964. CW laser on the VR transitions of CO I showed in 1965. It's only about 4 years ago now that coherent radiation is now producing CO laser at 5 micrometers. Let's go to that, I invented it in 64. Took almost 50 years to get to that stage. Wavelength is in 5 micron to 6 micron region, which is roughly half the CO2 laser wavelength. So the CO laser radiation can be focused down to half the diameter of radiation from a CO2 laser, which means you need only 1/4 the power of the CO2 laser for the same application. CO laser is electrically more efficient than CO2 laser. I won't go into the details why it is the case, but take my word for it that you can get almost 20 to 25% actual working efficiency from a CO laser. A CO2 laser typically provides 10 to 15% of electrical efficiency. So CO laser now is targeting many industrial applications, and the potential medical applications are not too far in the future. So two lasers, CO2 and CO, both which were invented in 1964-65 timeframe, are now some of them have been CO2 laser has been, CO laser is now becoming commercial reality. So high power lasers in the infrared, molecular lasers, pros are very high powered and large number of fixed wavelengths. Cons, very fixed wavelengths and coverage determined by the nature. A critical invention in 1994, some of these deficiencies. Something called a quantum cascade laser was invented at Bell Labs, which now can be tailored to any wavelength from 3.5 micrometers to terahertz, but high powers are not available. What you find is that QCLs can meet the requirement for tunable applications, but power output is roughly between 1 to 4 watts for QCLs versus hundreds of watts for CO2 lasers. For tunable application, you will need multiple lasers to cover the entire desired wavelength. And scan time can be fairly short, but we need to keep track of individual laser wavelengths as the lasers age because of wavelength stability and wavelength references. Fixed frequency lasers don't suffer from wavelength stability because that wavelength is fixed by nature. So for fixed wavelength applications, CO2 lasers, QCL just might replace CO2 lasers in some applications. What are the challenges? Challenge is 4 watt power output for QCL versus hundreds of watts for CO2 laser. But size and weight favor quantum cascade lasers. Potential applications are laser marking, a very big application, injection locking of high power CO2 and CO lasers, so that you can get stable multiple line operation of high power molecular lasers for more efficient power extraction. I said something about size, weight, and power favor QCLs. I show you typical picture. The top part here, this is a sealed off CO2 laser produced by Coherent. It generates roughly 4 watts of power output. Volume is 192 cubic inches. This is a 20 pounds, it's water cooled, requires 200 watts of input power. QCL, which is down here, this is down, what you see down here, is 2 cubic inches in diameter, in volume, weighs 2 ounces, it's air cooled and requires only 25 watts of input power. So you can see that for some applications, even for fixed wavelengths, QCLs may be of great use. So if I look at the laser power map today, the CO2 laser hasn't changed. What I put down here is the quantum cascade laser, which is started down here with very little power and reaching up to about 4 watts. Incidentally, I should point out that the 4 watt target, 4 watt power output that I mentioned was achieved at Pranalytica, my company, some years ago. So let me wrap up by saying CO2 lasers have been important in forefront research instrumentation for machining, metalworking, and welding, for medicine, for pollution detection, semiconductor clean room monitoring, and defense. Basically, my message here is CO2 lasers are everywhere. So, what did I learn from 1961 to today? This is my golden rule for success. You want to be smart enough to know that something is important, but dumb enough not to know that it is impossible. Ladies and gentlemen, thank you very much for your attention.
Good morning, all. So we have reached the end of today's webinar session. I deem it a great honor and privilege to propose a word of thanks for this great event, ROS 2023, organized by the Raman International Optronics Society, RIOS, in association with the Department of Optoelectronics, University of Kerala, India, and the LELS, University of Nova Gorica, Slovenia. On behalf of the RIOS and the entire organizing team of ROS 2023, I extend a hearty word of thanks to our distinguished speaker, Professor C.K.N. Patel, founder, president, and CEO of Pranalytica, California, USA, for gracing your important work and sharing with us your findings and opinions towards a talk on the genesis of the carbon dioxide laser and how it changed the world of lasers. I must mention our deep sense of appreciation for you, sir, for giving excellent coverage to topics such as carbon dioxide lasers and their technological applications, quantum cascade lasers, and challenges. Once again, we thank you, sir, for your outstanding presentation. A
Thank you.
special thanks to the chairpersons, vice chairpersons, secretaries, and advisory committee members for their encouragement, support, and coordination to make this webinar successful. We are thankful to all the eminent personalities, professors, faculties, and students worldwide who joined the webinar and participated actively. Thank you all for making today's event successful with your contribution.